Okay, let's dive into one of the most exciting frontiers in artificial intelligence today. It's a field called self-supervised learning, where AI is literally learning on its own, without us having to spoon-feed it millions of labeled examples. And right at the heart of this frontier, there's a huge battle going on between two very different methods. How this showdown plays out is going to shape how smart and, more importantly, how reliable our future AI will be. And that brings us to the big mystery we're going to unpack today. You have two AI models, they both seem really powerful, but when you throw them into the chaos of the real world, blurry images, noisy audio, complex scans, one of them thrives and the other one just completely falls apart. So why is that? What's the secret sauce that makes one work where the other fails? That's the puzzle we're here to solve. So first, just a quick refresher on self-supervised learning, or SSL. The whole idea is kind of revolutionary. Instead of us teaching the AI what a cat is by showing it a million pictures labeled cat, the AI teaches itself. It might take an image, hide a little piece of it, and then its job is to guess what's in that missing piece. By doing this over and over, billions of times, it starts to build this incredibly deep, intuitive understanding of the world, all without a single human label. It's pretty amazing. Okay, so back to our mystery. In our investigation into why some AIs can handle messy data and others can't, we've got two main suspects. These are the two dominant approaches to SSL. So let's meet our contenders. You can see the fundamental difference right here. On the left, we have Reconstruction. Its goal is to take a modified input and rebuild the original perfect version. On the right, we have Joint-Embedding. Its goal is different. It gets two different views of the same thing, say a cropped picture and a color-shifted version, and it just has to realize, hey, these two things represent the same core concept.
I think a fantastic way to think about this is like a perfectionist artist versus an abstract thinker. The artist, that's Reconstruction, it is obsessed with getting every single tiny detail right. Every pixel has to be perfect. It's working in what we call input space, the raw data itself. But the thinker, Joint-Embedding, it couldn't care less about the individual pixels. It's trying to capture the abstract idea, the vibe of the image. It operates in the latent space, which you can think of as the AI's internal world of concept.
Now, to be fair, our perfectionist artist is an absolute genius at certain tasks, especially language. I mean, think about it. If you want an AI to predict a missing word in a sentence, it has to understand everything: grammar, context, semantics. That intense focus on detail is exactly what you need.
But here's the catch. When you take that same perfectionist approach and apply it to images, that strength becomes a huge weakness. The AI gets completely bogged down. It spends all its time and energy learning the texture of a rug or the specific shade of a wall, because those things take up tons of pixels. It gets obsessed with these high-frequency details and totally misses the most important thing, like the cat sitting in the middle of the room.
So you're probably thinking, okay, case closed, the abstract thinker, Joint-Embedding is the clear winner, right? Well, not so fast. The problem isn't just about the method. It's about the world these AIs live in. And to really solve this puzzle, we have to talk about the unseen villain of this whole story: noise.
And this, right here, is where the research for this explainer drops an absolute bombshell. For decades, the answer to almost any problem in AI has been simple: just get more data. But this research proves that in self-supervised learning, that's just not true. You can throw mountains of data at your model, and it won't help one bit if your training process isn't aligned with the noise in that data. This is a massive, game-changing insight.
So to really get what's going on, let's nail down these three terms. First, noise. That's just any irrelevant stuff in your data: background clutter in a photo, static in an audio file, anything you want the AI to ignore. Second, augmentation. This is how we train the AI by messing with the data on purpose, rotating it, cropping it, changing the colors. And third, alignment. This is the secret ingredient. Alignment is when the augmentations you use to train the AI actually mimic the real-world noise it's going to face. So the whole theory hinges on this idea of alignment, that how we train the AI needs to match the kind of noise it's going to see in the wild. But that's the theory. What does the evidence actually show? Let's get to the good stuff. Okay, you have to see this. This chart is basically the smoking gun of the whole investigation. Focus on that bottom row, the one labeled strong noise. Now on the far left, for regular supervised learning, the lines go down. That means more data makes it better. Classic. But now, look at the two SSL methods. See those blue and orange lines? They are completely flat. Adding more data, moving from left to right, does absolutely nothing, zero. Only the green line, the one with strong alignment, actually shows any improvement. This is the proof.
And here's the bottom line from that chart. When the data gets really noisy, Reconstruction's performance doesn't just get a little worse. It totally collapses. It's just too focused on all those noisy, irrelevant pixels. But Joint-Embedding, our abstract thinker, it holds up way, way better. It's already built to ignore superficial details, so it's naturally more robust to the chaos.
And this visual, this gives you a peek inside the AI's mind. That third panel shows a healthy AI. All the different concepts are neatly organized into colored clusters. The fourth panel, that's what happens when you hit it with strong noise. It's pure chaos. The AI is completely lost. But then, look at that final panel. By training the AI with augmentations that match the noise, it's like we gave it a pair of noise-canceling headphones. The order is restored and clarity returned.
And if those visuals weren't enough, here are the cold, hard numbers. When you feed these models corrupted images, MAE, which is a top-tier reconstruction model, sees its performance absolutely tank by over 25%. Now compare that to DINO and BYOL, which are joint-embedding models. Yeah, they take a hit, but their performance drop is less than half of Reconstruction's. I mean, the evidence here is just undeniable.
So there we have it. The mystery is pretty much solved. We know why one method can handle the messiness of the real world and why the other often fails. Let's just wrap this all up with the final verdict and talk about why this is so incredibly important for the future of AI. All right, here are the key takeaways you need to remember. If you're working with super clean, low-noise data, sure, Reconstruction is a solid choice. But in the real world, where data is almost always noisy, joint-embedding is just far more robust and is definitely the way to go. And the golden rule, the single most important lesson here, is that for self-supervised learning, your training augmentations must be aligned with the noise in your data. Just getting more data is not the answer. It will not save you.
And look, this isn't just some academic thought experiment. Think about real-world AI. Medical scans have weird artifacts, satellite images have clouds, a self-driving car's camera has to deal with raindrops and sun glare. All of that is noise. Building an AI that is tough enough to handle that kind of unpredictable mess is what makes it a life-saving tool instead of a dangerous failure. And that's exactly why the robustness of joint embedding is such a massive game changer. So we've cracked a huge piece of the puzzle for making AI stronger today, but it leaves us with an even bigger, more profound question for tomorrow. You know, it's one thing to teach an AI to ignore things we already know about, like fog in a picture, but how on earth do we build an AI that's smart enough to figure out all on its own how to ignore the kinds of irrelevant noise that we can't even imagine yet? That is the next great mystery.